Hi, this is Barrett Givens, and in this video, we're going to talk about a connection between topology and real analysis. So we've already been talking about the concept of a limit point, but we're going to take it one step further and talk about a limit of a sequence, okay? So if you have a sequence of points, so that's not just like a set, that's a collection of points where they go in sort of an order. You have x1 first, and then x2, and then x3. So you're kind of imagining traveling along this sequence of points. A sequence of points in a topological space X converges to little x in capital X. So converges to is the term that we're defining here. A sequence converges to little x if and only if for every open set U containing x, there is a capital N in the natural numbers such that for all little n greater than or equal to capital N, x sub n is an element of U. All right. If you've taken a real analysis class, this should maybe sound a little bit familiar. This should sound a little bit like the definition of the limit of a sequence of points in real analysis, okay? The only difference is that in real analysis, there would probably be an epsilon somewhere, right? In real analysis, a lot of the definitions involve for all epsilon greater than 0, there exists a delta or there exists an n, something like that. So this topological definition has kind of eliminated the epsilon. We don't need epsilon anymore. The open set U is kind of taking the place of epsilon, okay? And in the standard topology on the reals, it turns out that that's pretty much the same thing because open intervals on the reals look like, or open sets on the reals, I should say, look like open intervals. And so you might take an open interval to look something like, here's my x, take an open interval around it. I can write that open interval in the form x plus epsilon, x minus epsilon, or at least I can find an interval, maybe contained in a bigger interval that looks like this. And so that's how there's a connection here between what's happening in real analysis and what's happening in topology. So in topology, we don't want to talk about the epsilons. So we're going to get rid of those. And we're just going to call this U, okay? In the standard topology on R, U really does look like an x minus epsilon, x plus epsilon, or something close to that anyway. But in other topologies, the U might be something very different. And so the advantage is that this definition can apply in a lot more different situations, whereas the real analysis one is really just for on the real number line, okay? But you can see how they're related. All right. So that's the definition of converges to. Let's do a couple of examples, one with the standard topology and one with the lower limit topology. All right, so let's show that x sub n equals 1 over n converges to 0 in the standard topology on the reals. Okay? So that means I'm going to be looking at my capital X is all reals. My little x is what the sequence is converging to, which is 0. So I'm going to look at my number line. There's my number 0. And the definition says I want to think about every open set U containing X. So let me also draw the points on this sequence here. I'm going to zoom in a little bit. So here's 1, 1/2, 1/3, 1/4, and so on, right? So now let's take an open set. Let's take an open set in the standard topology. Well, in the standard topology, an open set is an open interval. So I'm going to take an open interval that contains 0. So here's my U. And U goes from A to B, where A is less than 0 and B is greater than 0. And I want to claim that there's some capital N where for all little n greater than or equal to capital N, all of these points in this sequence are inside of that interval. So I'm looking at there is some capital N such that for all little n greater than or equal to capital N, x sub n is in this U, okay? And the U just has to be arbitrary. I just had to write it as A and B because it says for every open set U, okay? So what can I do? I can do this in a couple different ways, depending on how strict I want to be. One way is I could say, well, we already know from calculus that the limit of 1 over n is equal to 0. And so that means that at some point, they're all going to be there's, from some point on, all of the terms in the sequence will be less than B. Or I could actually do like an analysis epsilon style proof in this case if I want to. Yeah, let's do that. I'll do it sort of like the long way. Okay, so we're going to pretend that we don't know that 1 over n converges to 0 and sort of show how we would do it and how it looks just like an analysis style proof. All right, choose capital N so that 1 over capital N is less than B. Then let little n be greater than or equal to capital N. Then x sub n, which equals 1 over little n. Okay, I want to compare these two. 1 over little n and 1 over capital N. Which one's bigger and which one's smaller? Well, capital N is the smaller integer, so 1 over capital N is the bigger fraction, right? Bigger integers make smaller, like bigger denominators make smaller fractions. Okay, and then this is less than B. So x sub n is in U for all little n greater than or equal to capital N. Okay, and so I took an arbitrary open set. An arbitrary open set in this case is an open interval, and the top side of the interval is a positive number B, so I can choose a capital N so that 1 over n is less than B. That's like the Archimedean property. I let little n be greater than or equal to capital N, and I did a little bit of analysis style inequalities to show that x sub n is in U for all of the n's after some capital N. All right. That should very much remind you of limit proofs in analysis. Okay, now what about this second example? Let's look at the sequence 1 minus 1 over n. 1 minus 1 over n. So in the standard topology, what is the limit of that? In the standard topology, the limit of that sequence, just using calculus, 1 over n goes to 0. So 1 minus 1 over n approaches 1 minus 0, which is 1. So you'd think it would converge to 1. But then the next part of this problem says, show that it does not converge to 1 in the lower limit topology. So the point is that the convergence facts that you know are true in the standard topology, but might not be true in other topologies. So I have to show it does not converge to 1. So looking at the definition, to show that it doesn't converge, I can use sort of like De Morgan's laws. The statement here says it converges if for every open set, there is a capital N, such that for all little n, blah, blah, blah. Okay? So what we want to show then, we must show the negation of that. We must show, instead of saying for every open set U, we want to say there exists an open set U such that for all capital N, there exists a little n greater than or equal to capital N, such that y sub n is not in U. So I took the negation of the definition of converges to. I took the negation of that. That's what I need to show, okay? So let's draw a number line also. Here's my number line. Here's the number 1. The terms of the sequence, when n is 1, I get 0. When n is 2, I get 1 minus a half is a half. When n is 3, I get 1 minus the third, which is 2/3, 3/4, and so on. In the standard topology, it does approach 1. So they're getting kind of closer and closer to 1 in the standard topology sense. All right. And I need to find an open set. And I should have said here, containing 1. Containing 1. So I need to find an open set that has the number 1 in it, but none of these, like these y's are frequently not in there. Okay, like for no matter how far out you go, there's going to be some that are not in there. All right. And what I have to remind myself, what do the open sets look like in the lower limit topology? The lower limit topology is the one that's formed by intervals of the form AB, where A is included and B is excluded. Okay, it includes the lower limit. So the open sets look like this. Okay, that's an open set in this topology. So can you find an open set that includes one, but doesn't include the terms of the sequence? I think so. What am I going to do? I'm just going to take that right there. I'm going to make my open set just go from 1 to some value. So let's let U be the open set 1 to 2, including 1, but not including 2. Then Y sub n is not in U for any n. So that shows that Y sub n does not converge to 1. Okay, so we have this connection with real analysis in that we talk about limit points, and then when we're talking about a sequence, we can actually talk about a sequence converging. And in the standard topology on the reals, that turns out to be basically the same idea that we had of a limit of a sequence in a real analysis class. And so this idea of a sequence converging in the standard topologies matches up with what you've learned previously. But when you have a different topology, it might be a completely different concept of converging. And so like in this example, for example, here's a sequence that seems like it should converge to 1. Our intuition says it could converge to 1. But because this topology is different, we really have to use the definition. And when we use the definition carefully, we see that, in fact, it does not converge to 1. And so I actually claim that this sequence doesn't converge to anything in this topology, which is, strange. And so that's one of the fun things about topology, I think, is that the different topologies can give you very counterintuitive statements. All right. Thank you.